So, design lab experiment number one. So, it is a VAT governor. Aim to study the performance characteristics of a VAT governor and to find the relation between force and radius of rotation, speed and sleeve displacement, and also to find sensitiveness. Procedure: arrange the governor mechanism under the test as required configuration. This can be done by fitting the chosen sleeve as per configuration. Connect the motor to the speed control or the thermostat using 4-way cables and switch on the supply. Measure and note down the initial radius of rotation, length of link and initial height of the governor. Increase the speed gradually using thermostat provided until the center sleeve rises of the lower stop aligns with the first division on the graded scale. Record the position and speed. Fourth point, increase the speed gradually to have stable sleeve displacement and note down the sleeve displacement according throughout the range of sleeve movement possible. Fifth point, calculate the value of stability and sensitiveness of the governor. Sixth point, plot the governor characteristics curves using the data tabulated in the tabular column. Precautions: increase the speed gradually, take the sleeve displacement when the pointer is steady. Ensure the load on the sleeve does not hit the upper sleeve on the governor. Bring the dimmer to zero position. Next, observation. So first is length of the link, small EL equals to 130. B, initial height of the governor H0 equals to 90 mm. C, initial radius of the rotation R1 equals to 135 mm. D, mass of the ball assembly is 0.5 kg. E, minimum equilibrium speed N1 is dash RPM. F, maximum equilibrium speed, that is N2 equals to dash RPM. And weight of the sliding sleeve is 1.2527 kg. This is the universal governor apparatus. So this is a motor. Here we have the governor. So the governor right now it is set up. So there is no center weight. So it is a VAT governor. So these are the ball assembly. These are the sleeve arms. So the sleeve arms are 130 mm. From here to here, measure it from here to here. The sleeve arms are 130 mm. The initial radius of rotation is half of this, that is from here to here. It's called as the R0, H0. That is H0. This is a height. Initial height of the governor H0 is 190 mm. And this is initial radius at the rest. So this is the initial radius of rotation, this R0. So the sleeve displacement, so when the governor turns, the sleeve rises, so the sleeve displacement measure on this vertical scale. Next, so conduction, so we have to measure first. We have to start the machine. So draw a tabular column showing serial number, governor speed in RPM, angular velocity omega, sleeve displacement x, height h, initial angle of inclination alpha, radius of rotation r, and force F. So first we have to note down the sleeve displacement and corresponding governor speed from the apparatus. So sleeve displacement we will mention, we will take 10, 20, 30, 40, 50 noted values. For this sleeve displacement we will note down the speed RPMs. So now we'll carry on the experiment. So now we'll start the machine. Let's start the experiment. So slowly increase the on the thermostat speed of the governor. Slowly increase. Now before lifting, note down the minimum equilibrium speed N1. So minimum equilibrium speed means when the sleeve begins to rise. For the initial, the sleeve begins to rise. When the sleeve begins to rise, note down the RPM. This is the initial equilibrium, minimum equilibrium speed N1. So this is the minimum equilibrium speed N1 302.5. Now slowly increase the thermostat to increase the speed of the governor to get the maximum equilibrium speed N2. So when the sleeve reaches the maximum point, so this speed is called the maximum equilibrium speed N2. And note, measure the speed on the motor. So this is 510, 515, 510.3 RPM. Now slow down the governor. Now for 10 mm rise, so now for 10 mm rise, note down the speed for 10 mm rise, for 10 mm displacement, note down the speed, that is 323.4. So write down the minimum equilibrium speed, so that is 305. So divide by 2 because of it is the motor speed and the governor speed is half of the motor speed, that's why 155. Similarly, note down the maximum N2, that is 600. So divided by 2, that is 300 RPM. This is maximum equilibrium speed. Now for 10 mm rise, note down the governor speed, that is half of the motor speed. Now similarly for 20 mm rise, note down the speed. This speed should be half motor. This is the motor speed, and take half of this. So take half of this to get the governor speed. So for 20 mm rise, write the governor speed. Now for 30 mm, rise, note down the governor speed. So divide it by 2 because half of this is governor speed. This is motor speed, half of this is governor speed, divided by 2. Write it under 30 mm, write the RPM. Similarly, increase the thermostat and make the sleeve steady at 40 mm. Note down the speed. So make half of it divided by 2, 350 divided by 2. So for 40 mm, write down the speed. Now for 50 mm rise, note down the speed. So this is motor speed divided by 2 is the governor speed. So divided by 2 and write down for 50 mm, write down the governor speed. So now stop the experiment. Now the calculation. So after finding the speed for 10, 20, 30, 40, 50 mm displacement movement, now calculate angular speed. So angular speed or angular velocity omega is calculated by the equation omega equals to 2 pi n by 60. So for the first reading, 2 pi n, for the first reading n is 160. So 2 pi n 160 by 2 pi 160 by 60. So we get the angular velocity omega 16.75 radians per second. Similarly, calculate for all speeds 2 pi n by 60 for all the RPMs, governor speeds. Calculate the angular velocity. Next, to find the height, instantaneous height. So to find the height for the first reading, height is given by the formula. Instantaneous height formula is given by h equals to h naught minus r x by 2. It's x by 2. H naught, that is the initial height of the governor, minus x is the displacement, by 2. So we get 88. Similarly, calculate it for all the readings. x h naught minus x is 20 by 2, we get 83. H naught minus 30 by 2, we get 78. H naught minus 40 by 2, we get 73. H naught minus 50 by 2, we get 68. So we get the incidence height for all the readings. Similarly, angle of inclination. Now, angle of inclination, we have the formula alpha equals to cos inverse h by L. So cos inverse, the instantaneous height h, and L is the length of the link, that is 130. So we get the angle. Similarly, calculate all the angles for all the readings. Now radius of rotation R is, the formula is 50 plus L sin alpha. 50 plus L is the length of the link, sin the corresponding alpha. So substitute all the values of alpha, we get the corresponding radius of rotation R. Similar, and lastly, the force, centrifugal force F. Controlling force of centrifugal force F is M plus capital M omega square R. M is the mass of the ball, capital M is mass of the empty sleeve, omega square into R by 1000. M is 1.0.72 plus capital M is 1.72 kg. Omega 60.75 the whole square into R is the radius of rotation for the first reading 138.77 divided by 1000. So we get 94.99 newtons. Next, governor effort Q is C into M plus M into G. So C is change in speed, we get it from the formula N2 minus N1 by N. So N2 is the maximum equilibrium speed, N1 is the minimum equilibrium speed by N1. So we get C. So M is mass of the ball, small m is mass of the, capital M is mass of the empty sleeve, into G is acceleration due to gravity, 9.81. Substitute, we get the Q. So we get the Q value. Governor power is P equals to Q into X max. So Q value into X max, maximum and displacement X max. So we get governor power. Lastly, sensitiveness of governor, N2 formula is N2 minus N1 upon N2 plus N1 by 2. We get sensitiveness of governor. So lastly, write the result. Governor effort Q equals to N governor power